Global electrical grid modernization is colliding with a critical chemical bottleneck. Regulators are forcing a rapid phase-out of sulfur hexafluoride, the most potent greenhouse gas known. The primary replacement for high-voltage applications is fluoronitrile, known as C4-FN. However, the supply chain for this eco-gas is facing an immediate capacity cliff. The data illustrates a severe structural divergence. By 2030, global demand for C4-FN will reach 4,000 metric tons. Yet, the primary global producer, 3M, is exiting all fluorochemical manufacturing by the end of 2025. This exit drops global capacity to just 400 metric tons in 2026, triggering a 900-ton deficit. Commissioning lags for new high-pressure reactors mean this deficit will persist through the decade. This chemical deficit is translating directly into grid infrastructure delays. Lead times for SF6-Free high-voltage switchgear have doubled since 2020, reaching 120 weeks. At the same time, the capital cost premium for these units has surged to 45%. Utilities face a dual penalty of extended project timelines and escalating budgets. These cost increases are driven by fundamental physical differences between the gases. C4-FN has lower low-temperature performance than sulfur hexafluoride. To compensate, equipment manufacturers must design larger, high-pressure multi-chamber enclosures. This increases the volume of specialized aluminum and steel required per unit. The physical reality of chemical substitution is inflating the cost of grid decarbonization. The transition presents a stark trade-off between environmental performance and supply chain security. C4-FN mixtures reduce global warming potential by 98.5% while retaining 95% of the insulating strength of SF6. This makes it the only viable chemical for high-voltage transmission. However, its supply chain concentration index stands at an extreme 85 out of 100. Alternative technologies like dry air eliminate supply chain risk, but carry a severe physical penalty. Dry air has less than half the insulating strength of SF6. Using it requires massive equipment footprints, which is impossible in space-constrained urban substations. This structural lock-in to a highly concentrated chemical supply chain mirrors the mid-20th century phase-out of polychlorinated biphenyls in transformers. When those toxic coolants were banned, utilities faced a decade-long scramble to redesign grids, proving that chemical transitions always dictate the pace of physical infrastructure.